Hi, this is Leetcode question. Apply operations to maximize score. This is the last question of weekly contest number 358. To solve this question, initially we have the answer equal to 1 and we need to maximize the score or the answer as much as we can. And because we are multiplying, or we will multiply the answer by numbers from the array, the best thing to do is to take advantage of the values or the numbers that has maximum value. So we start with this number because we will multiply the answer by this value. We need to use it as much as we can. Now, how many sub-arrays that has 30 as the maximum prime score? Let's assume some number which is 8, and so because 8 is less than 13 we will use all of these 8, and so we will multiply the answer. So answer equal answer multiplied by 30 to the power 8. Now we used 8 operation from k, so after this k will be 13 minus 8, which is 5. And the next step is to move to the next maximum or next largest element in the array. In this case it's 10. Now again, how many sub-arrays in which 10 has the maximum prime factor? Let's assume some random number, which is 7. So we can use 10 7 times, but we need only 5 times. So in this case we will take the minimum of 5 and 7, which is 5. So answer equal answer multiplied by 30 or 10, a number to the power 5. Then k will be 5 minus 5 equals 0. Remember, these numbers are just it's not necessarily they are the correct numbers, just an example. So this is the procedure we will follow, and so we start with the maximum value, then the next, and so on. Now the question is, how can we know the number of sub-arrays in which the number has maximum prime factor? To do that, we need to calculate the score or prime score of each number, and we have this function prime score. So this function is the same implementation as the function that calculate the prime factor of a number, but here we just need to count the score or the number of unique primes for the given number. And so for number 1, the prime factors is there is no prime, so 0. 6 is 2 by 3, and we have 2 primes, so 2. 7, here we have only 7 as prime factor, so the score is 1. 30 is 2, we have 3 as score, and 10 is 2 multiplied by 5, which has 2. And so the first step is to create prime score vector for each of the numbers, and for each number we call prime score function. And time complexity for this function, if we given a number, is log or square root of n. So time complexity for this for loop, assume the number of elements in the array is n, and the maximum value of number in the array is m. So the time complexity is n multiplied by the square root of m. So after this for loop, prime score array is 0 and 2 for 6, 1 for 7, 3 for 30, and 2 for 10. And remember, our target is to find the number of subarrays where the number has the maximum prime score. And to do that, let's take this value and assume we want to calculate the number of subarrays in which 6 has the maximum prime factor. So all the subarrays until 3, since 3 is greater than 2, so any subarray that contains 2 should stop here or before. We should not include the 3, because if we include the 3, then this will be the max score. So this is for the right side of 2, and in the left side the same. We look for the first number that is greater than 2, greater than or equal. In this case we stop at -1 or index -1 here. So we include all these numbers, and this is for left side. So if we have index -1, which is outside the array, and the index here is 0, 1, 2, 3, 4, and 5 is outside the array. Now the next greater, or the first element that is greater than 2, is at index 3. The first element that is equal or less than 2 is at index -1. And notice that in the left side we are saying we are taking equal, because if there is number like 2 here, we should stop here, because 2 is equal to 2, and if we include both 2, this will be the number. So we need to stop here, and this should not be included. So after this we have left and we have right. So how many numbers in the right side? It's this index 3 minus the current index 1 equal 2. So this is R, and this is correct because we have two numbers, 1, 2, and in the left side we have index 1 minus -1, which is 2, and this is correct also because we have this number and this number. So we have 0, 2, 1, two numbers in the right side, two numbers in the left side. Now the question is how many subarrays we can form including this 2. The answer is L pi R, which is 4. So here you can take this subarray 0, 2 or this subarray 0 to 1, or you can start at 2, so 2 1, or 2 itself, which is 2. So for every element in the left side you can form a subarray with every element in the right side, so in total we have 4. So all what we need to do is to find left and right, and to do that, for every element in the array we need to find the first greater element in the right side of the element, and the first greater element, or the first element that is greater or equal to the current element in the left side. And this problem is popular, and it's solved by monotonic stack. So this is popular algorithm, and I will not explain it here. All what we will do is just find the next greater element for every index. So for 0, what is the first element in the right side that is greater than 0? It's 2. So because we are storing indexes, so this is index 0, 1, 2, 3, 4, 5 is outside, and this is -1. So for 0 the answer is at index 1. For 2, the first element that is greater than 2 is at 3. For 1, it's 3. For 3, it's 5, because there is no greater element in the right side of 3. For 2, it's 5. So this algorithm, monotonic stack, for next greater we will have this array at the end. Then we will do the same for previous greater. And for every element we will find the first element that is greater or equal to the current element. So for 0 it's -1. Here we are looking for the left side. For 2 it's -1. For 1, the first element that is greater than 1 in the left side is 2, which is at index 1. For 3 it's -1, because there is no element greater than 3 on the left side of 3. For 2 it's 3. That's it. This is the previous greater element. And notice for here we have less than or equal, and here we have less than, because for the next greater element we need to stop at the first element that is greater than the current value, while in the previous greater we need to stop at the element that's greater or equal. This is why we have to pop the elements that are equal here. So after these two loops we know the next greater and the previous greater elements. Next is, it's easy to find L and R for each number, and as we started we said we have to take advantage from, or we need to use the number that has the maximum value, and to do that we need the max priority queue, or you can sort an array both works. In this case here we have max priority queue, in which we push each number with its end with the index. So 30 at index 0 1 2 3 4, 30 at index 3 is the top of the priority queue. So we pop this element. We start with 30. Now what is the next greater element for 30? 30 is at index 3, so 0 1 2 3. The next greater element is 5. So r equal 5 minus the current index, which is 3, the index of 30, is equal 2. And how many elements in the left side of index 3? So what's the previous greater element at index 3? It's minus 1. 3 minus 1 is 4. So we have 4 elements in the left side of 3, and 2 elements in the right side of 3, which is true. So the right side has 1 2, the left side 1 2 3 4. Now the number of subarrays, as we said, is L multiplied by R equal the number of subarrays. In this case it's 4 multiplied by 2 equal to 8. So, and these 8 subarrays, so if we took all these number 0 2, then 1 3 2, we need to find all the arrays that, or subarrays, that include this number. It should be 8, and that's true because you can start with 0. You can take this subarray or this. For 2 also this or this. For 1 this or this. For 2 this or this, the 2 itself. So in total we have 8 subarrays. Now what is the value of k? K equal 13, so we need to use the whole 8 numbers after that. So answer, or let's put answer here, equal answer multiplied by 30, original number, multiplied by 8, or to the power 8, 30 to the power 8. Then we subtract 8 from k, so k now equal 13 minus 8, and this is 5. The next greatest element in the array is 10, which is at index 4. 10 at index 4, so this is 0 1 2 3 4. This is index 4. What is the next greater element? It's 5. So L or R equal 5 minus the current index, which is 1. L equal 4, the current index, minus previous greater element at 4 is 3. 4 minus 3 equal 1. So L multiplied by R, which is the number of subarrays, equal 1, and this is true because for this index you can only have this subarray, because if you include any subarray, any numbers other than this will be larger, or this has prime score greater than 2. So this is the only subarray we need, and so we multiply also to the answer the current number 10 to the power 1, and we subtract 1 from k, so 5 minus 1 equal 4. The next highest number is 7 at index 2. At index 2 the next greater element is 3, so r equal 3 minus the current index I, which is 2, and this is what we are doing here, and this equal 1. L equal 2 minus the previous greater element at 2, 0, 1, 2 is 1. 2 minus 1 equal 1, so L multiplied by R equal 1, so we multiply the answer by 7, original number, the number of subarrays, which is 1, and we subtract 1 from k, 4 minus 1 equal 3. The next value is 6, which is at index 1. The next greater element at index 1 is 3. That means R equal 3 minus 1 equal 2. L equal 1 minus the previous greater element at index 1 is minus 1. Minus 1 equal 2. So L multiplied by R equal 4. And here we need only 3 operation because k equal 3. So in this case we use 3 from this. So min of 3 and 4 equal 3. So we multiply the answer by the original number 6 to the power 3. Then k equal 3 minus 3 equals 0, and we are done. So this will be the final answer. Now the last question is how we calculate the power of number. So 30 to the power 8. Let's say we have 10 to the power 4, or 10 to the power 4. 10 to the power 4, 10 to the power 4. How can we calculate this? We need an efficient way, and this is why we are using this function k power n, which has log time complexity instead of iterating over every number and multiply it. So we have 10 to the power 4. This is the so k is the original number. This is k, and n is the because we are doing 10 to the power 4 to 10 to the power 4, so this is n. 10 to the power 4 equal n. Now we cannot iterate over all these value and do 10 to the power 4 multiplied by 10 to the power 4 and so on, because this will give problem for time complexity, because we are doing this with every number. And so here we are splitting the value. We are saying 10 to the power 4 to the power 10 to the power 4. This equal 10 to the power 4. What is the half of this? It's 10. to the power 4 divided by 2, and this is 10 to the power 4 divided by 2. So we kind of splitting the problem into halves every time, and we use recursion. So instead of solving for this number, we solve now for this number.